All right, today we're diving into the really strange world of nonmetals. Now, this is a group of elements that, well, it includes the air we breathe, the stuff in your pencil, and the hardest jewel on Earth. Yeah, they completely defy any easy definition. And honestly, that's what makes them so cool. So let's just jump right in with a puzzle. What in the world do the hardest jewel you can imagine and the softest stuff you write with have in common? I mean, a diamond and the graphite in a pencil, they're complete opposites, right? Well, believe it or not, the answer is just one single element. And if we can figure out how it pulls off this magic trick, we'll basically unlock the secrets of all nonmetals. Okay, so here's the game plan. We're going to meet the nonmetals, figure out their rules of attraction, talk about some seriously cool elemental shapeshifters, look at 3 big examples, and then see how all this stuff leads from pencils to, well, nanotubes. All right, let's get into it. Section 1, meet the nonmetals. And you know, there's so much more than just not metals. They've got a whole identity of their own. So if you look at a periodic table, you'll find this whole family kind of tucked away up in the top right corner. That spot really separates them from the huge majority of elements, which are metals. And their properties, oh, they could not be more different. You know, you think of metals as shiny, solid, good at conducting electricity. Nonmetals are just a completely different beast.
And what a beast it is. I mean, just look at this variety. It's kind of nuts. At room temperature, more than half of them are gases, like the oxygen and nitrogen all around us. There's only one liquid, bromine, and then you have the solids. But even here, they go to the extremes. You've got fluorine, which is the most reactive element there is, but you also have the noble gases, which are the least reactive. And get this, they can form the softest solids you can think of and also the absolute hardest. Talk about a study in contrasts.
So you gotta ask, what's the secret? How can one group of elements be so all over the place? Well, it all boils down to chemistry, which brings us to section 2, the rules of attraction. We're about to find out how these nonmetals, hook up with other elements and with each other. Okay, so nonmetals have this thing called high electronegativity. It sounds complicated, but all it really means is they are super greedy for electrons. They just love to pull them in. So when a nonmetal bumps into a metal, it's basically an electron heist. The nonmetal just yanks an electron away. That's called an ionic bond. But what happens when 2 nonmetals meet? Well, they're both greedy, so it's like an arm wrestling match where nobody wins. They end up having to share the electrons, and that's a covalent bond. This sharing is the real key to understanding why they can form such crazy structures. Now, to keep track of all this electron swapping and sharing, chemists use something called an oxidation state. Just think of it like a scoreboard for electrons. If an atom kind of loses its grip on an electron in a bond, its score goes up. If it gets a better grip, its score goes down. It's a really neat way to see exactly what an element is up to inside any compound. And this whole idea leads to some pretty clear rules of behavior. First off, nonmetals oxidize metals. That's that electron theft we were just talking about. Second, there's kind of like a playground bully rule. The more electronegative nonmetal will always win against a less electronegative one. It'll just take its electors. And the biggest bullies on the block? Fluorine and oxygen. They are the strongest oxidizing agents there are, period. And that makes their negative ions super, super stable. So yeah, it all comes down to a pecking order of who wants electrons the most. Okay, now this is where things get genuinely weird and really, really cool. Section 3 is all about elemental shapeshifters. The official chemistry term is allotropes, and you're going to want to buckle up for this one because it's the totally mind-bending idea that one single element can live completely different lives. So what is an allotrope? Well, imagine you have a box of Lego bricks. You can build a car, or you can take it apart and build a house. It's the exact same bricks, the same atoms, just put together in a different way, a different blueprint. And as we're about to see, changing that atomic blueprint, well, it changes absolutely everything. And a lot of nonmetals do this. You've got oxygen, which exists as the O2 we breathe, but also as O3, which is ozone, way up in the atmosphere. Phosphorus has white, red, and black versions. Sulfur has a whole collection of different outfits it can wear. But the undisputed king of all the shapeshifters has got to be carbon. Its list of forms just keeps getting longer. So let's really see this in action with a few key players. Welcome to Section 4, a tale of 3 elements. We're going to zoom right in on carbon, phosphorus, and sulfur to see just how wild these differences can get. And first up is carbon. This is it. This is the element that's going to answer that question we started with, the one about the pencil and the diamond. It is, without a doubt, the element of extremes. So what is the difference? Remember, it's not the atoms, it's the architecture. In a diamond, every single carbon atom is locked into this incredibly strong, rigid, three-dimensional web with four others. It's basically one giant perfect molecule, which is why it's so unbelievably hard. But graphite? Totally different story. Its atoms are arranged in flat sheets, like pages in a book. And these sheets are only weakly held together, so they just slide right off one another. That's why it's soft and slippery and perfect for writing. And this one structural change also explains why diamond won't conduct electricity, but graphite will. It's all about how the atoms are arranged. Okay, next up, phosphorus. Its name literally means light bringer in Greek. Why? Because one of its forms actually glows in the dark right before it bursts into flame all by itself in the open air. So yeah, you can bet its other forms are a little more chill. Yeah, phosphorus has two main personalities, white and red. White phosphorus is the dangerous one. It's made of these little four-atom molecules that are super strained and just dying to react. It's toxic and so dangerous it has to be stored underwater. But if you gently heat it, those little molecules link up, forming long, stable chains. And that gives you red phosphorus. It's a completely different substance. This is the stuff on the side of a matchbox. It's way safer, pretty much non-toxic. Same element, but one is a villain, and the other is a helpful tool. And for our last case study, we have sulfur. And if you thought the others were strange, sulfur just takes it to a whole new level. It has some of the most complex, most visually wild allotropes of any element. Seriously, watching what happens when you heat it up is like watching a chemistry magic show. Okay, so follow this. At room temperature, sulfur is this yellow, crystalline solid made of these cute little 8-atom rings. You melt it, and you get a thin, yellow liquid, still made of those same rings. But then you keep heating it, and suddenly the rings snap open. They start linking together into these super long chains. The liquid turns dark red and gets thick and goopy like molasses. And then, and this is the best part, if you take that gooey mess and dump it into cold water, the chains get flash frozen in a tangled jumble, and you get this weird, stretchy, rubbery stuff called plastic sulfur. It's incredible. So look, these elemental quarks are awesome, right? But this isn't just a fun chemistry lesson. There's a point to all this. Why does it matter today? Well, that brings us to our final section, from pencils to nanotubes, because it turns out these fundamental little arrangements are literally building the technology of the future. You know, for the longest time, we thought we had carbon all figured out. Diamond, graphite, that's it. But then Richard Smalley and his colleagues found something amazing. They discovered that there were other forms of carbon hiding in plain sight, in soot. Just the stuff from a smoky flame. This discovery of these new molecules totally blew the doors open to a whole new world of materials, like buckyballs and carbon nanotubes. And perhaps the most mind-blowing of them all is graphene. So what is this miracle material? Get this, it's just a single, one-atom-thick layer of graphite. That's it. For decades, physicists said it was impossible to get a stable sheet that thin. Then, in 2003, a couple of researchers finally did it. And you will not believe how. They took a chunk of graphite and some Scotch tape. I'm not kidding, regular office tape. They just kept peeling off layers until they got down to one. That simple little trick won them the Nobel Prize. And the properties of this ridiculously simple sheet of atoms are just staggering. It's practically weightless, but it is the strongest material ever tested. It's actually harder than diamond. I mean, they say a sheet of graphene as thin as cling wrap could hold up a full-grown elephant. It also conducts heat and electricity better than almost anything. This just impossible combination of properties makes it a game changer for everything, from ridiculously fast computer chips to crazy strong, lightweight stuff for planes and even body armor. And that brings us right back to where we started. We went from the simple carbon in a pencil all the way to a single sheet of atoms that could literally change our world. It just goes to show you that even inside the most common, everyday elements, there are these incredible secrets just waiting to be found. All you have to do is rearrange the atoms. So that leaves us with one final, huge question. Now that we have these new, unbelievable building blocks, what on earth are we going to build next?